All right, on example 5 here, let A and B be acute angles in a right triangle. Use a calculator to approximate the measures of angle A and angle B to the nearest tenth of a degree. And on the first one, it says the sine of A, remember that A as the input sign is supposed to be an angle, is equal to 0.87. So this 0.87, it came from somebody putting in their calculator probably for a right triangle the opposite of the hypotenuse and got 0.87 after it got divided. All right, so what we have to do is we have to untrap the A, the angle, from this sine. What do? How do we get rid of the sine that's right there? Can we just divide sine on both sides? No, we can't do that because this is not multiplication right here. The only time that you divide whenever you're solving an equation is if multiplication was involved, because that's the inverse. So for example, if I have 3x is equal to 12, if I'm going to solve that equation, I got to get rid of this 3. The 3 is multiplying by the x, so to get rid of it, we divide both sides by 3, right? And then we get x is equal to 4, I'm pretty sure. Okay, so yeah, division, it's off the table. So is multiplication, so is adding, so is subtracting, because that's not the inverse of what sine is doing here. Okay, so let me relate it back to the quadratic case here. I think this is really going to make sense because you don't see it happen with this super simple linear function. Actually, that's not a function, it's an equation. Okay, so if I have x squared is equal to 36, and then I want to solve that for x. I need to get this x out of the squaring function. I do the inverse. There's no division that happens here. What I'm going to do is I'm going to take the square root of both sides. When I take the square root of both sides, notice what happened here is my original function went inside of its inverse. That's called composition. Composition of functions. I put one function inside of another function. I have my function, and I put it inside of its inverse function. The way that this is read is f inverse composed with f of x. This is the definition of an inverse function. It gives you, if they're inverses, it gives you the original input back. So another fancy way of saying is that inverses cancel each other out and gives you your original input back. So what happens over here, of course, is that on the left-hand side, the square root and the square will cancel, giving me just x is equal to, and then the square root of 36 is 6. All right, it's actually a little bit more complicated than that, because the square root, as we saw, is not the true inverse of x squared. It's only part of it. The other part we just delete out. Now, isn't there another number you can square and get 36? Yeah, there's two numbers you can square to get 6. One's 6 and the other one is -6. But your calculator's never going to give that to you because it's outside of the output value for this inverse function, the square root. Here, let me show you on the calculator. So if I were to take something like the square root of 6 and then I square it, those two things should cancel each other out. Look on the far right hand side, it says 6, and it does. So the square root and the square canceled, I just got 6 back. But what if I did the square root of, in parentheses, -6, and then I did the same thing. I got an arrow out of these parentheses. It says undefined right now because, yeah. And then I square that guy, and you'd go, yeah, that should cancel out and give me -6 back. But it doesn't. It gives me +6 back. Why does it give me +6? Well, one way to think of it is that the square got rid of the negative and made it +36, and the square root of positive 36 is still 6. But another way of thinking of it is that the output of the square root function is only positive numbers because we got rid of all the negatives. It's this kind of limitation with inverse functions. In order to make them inverse functions, we have to sometimes delete part of the answers. Okay, so it's way worse with sine, of course, as we saw from the graphs. And let's go ahead and focus on number 1 here, which is the sine of A. Sine of some sort of angle A is equal to 0.87. And I want to untrap the A from the sine function. So sort of like what I did up here, I am going to compose sine with its inverse. I'm going to do this kind of thing right here. I'm going to take my sine function and I'm going to put it inside of its inverse, which is the inverse sine. It's called just taking the inverse sine of both sides. If I do it on the left, I have to do it on the right. Let me kind of scooch this over like so. On the left-hand side, these guys cancel each other out as they're supposed to, just like this thing, and it gives me a back. Now there's a little bit of a complication here, and that is they're only going to cancel each other out over the interval from negative 90 to positive 90. I'll show you in a second what that means on the calculator. So when they cancel each other out, it gives me a, and on the right-hand side, it gives me the thing I'm supposed to put into my calculator. Just like this gave me the thing I would put into my calculator. Inverse sine of 0.87. All right, so let's go to the calculator. Not that one, this one. Okay, and hit enter on this thing. And the inverse, I believe, is hidden under the functions menu. You can see sine, and then right underneath it, the sign little -1. That is the inverse sine. On your calculator, on the TI calculator, instead of hitting just sine, you hit second sine, and it'll pull up the same exact thing. All right, so inside here, you don't put the angle, you put the ratio, which is supposed to be, I think that was 0.87, right? And then I get about, I think it said round to the nearest tenth. So I'm going to report 60.5-ish degrees. So this is about 60.5 degrees. Okay, so let me explain kind of the same limitation for the inverse of sine. Like there was another angle here, or no, there was another x value that could have given us 36 once we squared it. There are an infinite number of angles that could have given us 0.87, something besides the 60.5. And it has to do with that periodic nature of the graph of sine. Oh, well, here's a copy of that thing, that it hits the same exact y value an infinite number of times. Okay, so on your calculator, I'll show you that like this. I'm going to try to do this business right here to cancel out my sine functions in order to get the original input back, just like I did with the square root. No, this guy right there. Okay. So let's hit enter on that. All right, so I'm going to do this kind of thing like the square root business, just with sine. I'm going to go with my functions, inverse sine. Inside of that, put the sine, so it's composition. And then in here, I'm going to put a degree measurement. Regular sine needs a degree. The inverse sine needs a ratio. All right, so I'm going to put in 30. So let me explain over here on the left-hand side. The sine of 30 is going to give me a ratio, and then the inverse is going to revert that ratio back to an angle measurement. Since these are inverses, they should cancel each other out and give me 30 degrees. Look over there on the right-hand side. It gave me 30. Perfect. That's exactly the way it's supposed to work. But watch what happens now. I'm going to do the exact same thing. I'm going to put the inverse sine of the sine, but instead of putting 30, I'm going to put 150 degrees. 150. And instead of just simply canceling out, it still gives me 30 back. Why did it do that? The reason why it did that is because 150 is outside of the output range for the inverse of sine, just like the negative numbers was outside of the output range for the square root function. So that's sort of the limitation that we talk about whenever we're dealing with inverses, whose true inverse of the original function is not a function, and we have to basically manufacture our inverse function by reducing the original domain. It happens all the time. All right, so that's really understanding trigonometry and algebra in a pretty deep level. All right, let's go and solve one last one, the cosine. Cosine, that's not a C, cosine of B is equal to 0.15. Okay, 0.15. All right, so again, I got this B, this is an angle, it's inside the cosine. I need to untrap it from the cosine by taking the inverse of cosine on both sides. So usually in practice, this is what we do. The proper notation is what I did up here, but just for a shortcut, I'm just going to do it like this, indicating that I'm taking the inverse cosine of both sides. On the left side, they should cancel each other out as long as B is between 0 and 180 degrees. and my b comes out of that situation, and I would get the inverse cosine of 0.15, and that's what I throw into my calculator. So enter inverse cosine, and I think it was 0.15, and I would report, since I'm asking to the nearest tenth, 81.4 degrees. All right, so let's see how that is used in order to solve for a missing angle measurement within a right triangle. I mean, that's the whole point of this thing, at least is the application that we're using it for in geometry. So here we go. It's a good old 3, 4, 5 right triangle, except for we don't even need 5. If the legs of a right triangle are 3 and 4, what is the measure of the angle opposite from the small side, which in the picture is marked as theta? All right, so the first thing that I want to do is probably erase the 5. I don't need it. I'm just going to use the information that was originally given to me. And I'm going to label my sides just like I did whenever I was solving for missing side with trigonometry. So according to my angle here, 3 must be the opposite side. And the 4 is the adjacent side. And then I go through my ratios and I go, oh yeah, this one is tangent. I'm going to use the tangent ratio. And I would write an equation like this. The tangent of, what's the input of tangent? It's an angle. And that's going to be theta, is equal to my opposite side, which is 3, and my adjacent side, which is 4. And now it's a problem just like what we solved right up here. I have to get this theta out of this tangent ratio. And so to do that, I'm going to take the inverse tangent of both sides. So on the left-hand side, they cancel. I want to actually do that. They cancel out, giving me theta back, which is what I wanted. And on the right-hand side, it gives me what I'm supposed to put into the calculator, which is the inverse tangent of 3 over 4. Let's throw that in and see what the calculator says. And right there, enter your inverse tangent of 3 over 4. You can, of course, type that in as 0.75 if you wanted to. And we get approximately 36.9 degrees. It's about 36.9 degrees. What's interesting is that this number right here, if I go back over here, those decimals go on and on and on and on forever. It's an irrational number. Like, the square root of 37, let's say. It's an irrational number. However, the sides, if I go back to this thing, the sides were just nice, neat whole numbers, and it seems to work that way. When we had irrational side measurements with the special right triangles, then we had, in those cases, some nice, neat whole numbers in order to compute the angles. Okay, that's crazy. All right, well, there we go. We've got the angle measurement here is 36.9 degrees, approximately. And then let's say that I wanted to find this angle. I'll call this thing alpha for right now. How could I find it? I don't need to set up another trig ratio. Remember that these two angles right here are complements of each other. And if they're complements, all I have to do is take this number and subtract that from 90 degrees. Sure, you could add this extra 90 in here, but that's extra. So I'm going to come back over here to my calculator, wrong calculator, this calculator, and I'm going to put in 90 minus my answer. On your TI calculator, that's second negative sign. I believe that pulls up the A and S, which is the previous answer. And you can see that this one is about 53.1 degrees. 53.1 degrees. And if I throw in the 5, what I've just done is I've solved that right triangle. I found every single side length and every single angle measurement that's associated with that triangle. And that is what's going to bring us to our second objective.